9CI is trying out a private testing facility RF chamber, located in our very own Cambridge. True RF facilities can have a cell phone tower antenna right outside their door and still have a background reading of 0. NEMCO is a public access facility that can be used outside of the university. With an antenna right across the road, no problem.
So we're in the NEMCO lab and we're just doing some quick tests. This is the gigahertz solutions meter that goes from 2.4 gigs to 10 gigahertz. So the test, as you can see, we're doing at a 1 meter distance, okay? And the test position is here. Transmitter antenna is there. So what we're doing, we're just adjusting the transmitter power to maintain a constant reference power level at this particular point in space. So our calculations are always that whatever frequency we go to, we're factoring in free space path loss, we're factoring in the gain of the antenna, and all the things that we know, and making it so that the power at every frequency that we're measuring here remains constant, and then whatever reading we're seeing on the screen relative to what theoretically is supposed to be there, that is the correction factor. So, and to do that, you need to be in an anechoic chamber. You need to be in an RF room that does not have reflections. And so this is a small chamber that's useful for these frequencies. Okay, so, and the same tests apply when we're testing the Safe and Sound Classic meter. We're putting the Classic in the test position here, and we can raise or lower remotely. We can raise or lower this transmitter antenna here to give maximum reading. Transmitter antenna can be rotated for polarization, everything like that. Even this whole pedestal that I'm standing on right now, it can be rotated if necessary. So everything can be done outside of this RF chamber for the calibration. And a room like this is required for RF testing calibration because these walls absorb RF and don't reflect them. I'm talking just maybe 10 or 15 degrees.
The orientation has to be correct, then measurements can begin.
Minus 3.6 dBm at 2.4 gigahertz, and we are reading...
Yeah, so 43, okay.
43.4 megawatts.
So now... Okay, so the next one, 4.4 gigahertz. We're doing 14.2 dBm.
4.4?
Yep.
What do you mean
14.2. 4.4 gigahertz, 14.2 dBm.
3.2 dBm.
So far, we're still within plus or minus 6 dB. That's good. So,
That's good.
again, compared to the crap that's out there, this is amazing. 5.4 gigahertz, we're going to 15.7 dBm.
Generators are doing the same values. Okay.
3.4 gigahertz and plus 2.6 dBm. Okay, 4.4 gigahertz and 4.6 dBm. Good. 5.4 gigahertz plus
36.
6.1 dBm. You're filming all this.
Oh yeah. Beauty.
What's the level?
Plus 6.1 dBm. 65, yeah, something like that. Okay, so now we're going to 6.4 gigs, and we're going to we're staying at the same power.
Okay, 15.7, staying at the same power?
Same power.
Okay.
Everything balances out.
Which
6.4 gigahertz.
6.4.
Yeah, we're just going up in 1 gigahertz steps.
We have also tested a reference meter.
2.4 gigahertz minus 3.6
Yeah,
dBm, pulse modulation.
So, square wave, 50%. I don't know whatever frequency. I don't know what if this thing will respond to.
So the pulse modulation frequency, we can put 100 hertz. It's okay. 100
Yeah,
hertz.
fine. Yeah, so we're just setting up the modulator, the signal generator because the gigahertz solutions meter does not do continuous wave measurements, CW. So we're setting up a 50% duty cycle square wave at 100 hertz. And once that's set up, we're going to start shooting RF at this thing at different frequencies, and just to see where things are at there with that meter. And I hope the battery doesn't die on it.
Oh yeah. It's not a bad battery.
That would be the thing to happen right now.
Oh no.